So space has entered a new era, an era where the most powerful machines are not single spacecraft, but are multiple satellites working together. And my research over the last 23 years and counting has been focused on making this distributed future real, from scientific discovery to critical infrastructure. So when I was 4 years old, a powerful earthquake in southern Italy changed my life, displaced my family, and made me realize how it's important to understand our planet as a dynamic system. And that eventually led me to space, because that's the key vantage point from which we can answer, or at least help answering, extraordinary questions. So what kind of questions? Questions such as, how do we prevent natural disasters? By measuring subtle changes of the shape and the mass of our planet. The UN counts in hundreds of thousands of life losses per year, the effect of natural disasters. Questions such as, how do we understand how planet and life form in the universe? NASA counts in 6,000 the exoplanets that we have discovered through indirect methods that we do not understand in terms of their habitability. Or questions such as space logistics. So how do we use space in a secure, in a safe, in a sustainable manner, given the proliferation of space assets? FCC counts in the order of 100,000 of maneuvers that are executed every year to avoid collisions in space. So these questions are at the core of disciplines such as planetary science, when we look down, astronomy and astrophysics, when we look up, and space logistics, when we look across. So in order to answer these questions, we have to overcome fundamental limitations dictated by the laws of physics. So what are these limitations? Limitations of resolution. So a satellite can be only that large in order to resolve tiny features in measurements and images. Or a satellite can have only that much propellant in order to move around. Or a satellite can only cover that amount of ground on the surface depending on its orbital position, depending on the sensors that are on board. And so this leads to the concept of distributed space systems. These are systems made of 2 or more satellites that interact and work together to accomplish objectives which are otherwise impossible or very difficult to achieve by a single monolithic system, to overcome that very fundamental limitations dictated by physics. So we classify distributed space systems according to the distance between the satellites on the x-axis, and according to how well we need to navigate these satellites with respect to one another to accomplish the mission objectives, and that's on the y-axis. And so at one end of the spectrum, we find constellations that pushes the limit of coverage. These are used for global navigation and communication. At the opposite end of the spectrum, we find rendezvous and docking that pushes the limits of mobility, for example, through orbital lifetime extension, repairing satellites, removing debris. This goes under the name of in-space servicing, assembly, and manufacturing. And in between, we find formations and swarms. These push the limit of resolution. Through formations and swarm, we can develop instruments which have an effective aperture, which is much larger than the individual size of the satellites, for example, through interferometry. Now, you can imagine the challenges that comes with these distributed space systems in terms of the autonomy of the individual satellites and the guidance, navigation, and control functionalities. And this is what my lab is there for, founded 12 years ago to enable future miniaturized distributed space systems. We do that through 4 pillars of research that operate in closed loop. in the first pillar, we conceive new mission concepts employing multiple satellites. So we derive requirements and objectives from these mission concepts that feed into the second pillar of research, where we develop those multi-agent guidance, navigation, control, autonomy, and decision-making algorithms to meet those objectives. These algorithms are then matured, tested on the ground, on our testbeds, using robotic and virtual reality, and then they are deployed in space on actual missions. And note that this is how we train our students. So we teach our students not just to study space systems, but to invent them, to test them, and to fly them in orbit. So let's have a look at some of our projects, starting from looking down, back at the Earth. And I start from really the first mission I worked on in my career, which is called GRACE, the Gravity Recovery and Climate Experiment, that has created the most accurate, time-varying gravitational model of the Earth, using 2 satellites flying in formation at 200 kilometers distance in low Earth orbit. They act as a spring that is sensitive to the tiniest changes of the gravitational field of the Earth. We are talking about milligauss, which is a millions of Earth gravity. And this spring allows us to measure depletion of underground water, allows to measure ice melting, allows to measure redistribution of water on a global scale caused by climate, allows to detect deep underground structures, something incredible that was enabled by some of my work here. The mission was launched in 2002 and operated for 15 years. And my task has been to develop the system to fly this formation, to control the motion within prescribed bounds, and exchange the order of these satellites during the mission, purely done from the ground. The second highlight is the TandemX mission. TandemX was launched in 2010 and is still operational today, employing 2 satellites which are identical, carrying 2 radars that illuminate the same scene on the ground to recover the 3D model of the scene. So this is called the digital elevation model, with an accuracy, local accuracy of 2 meters in height, global, independent from illumination condition and from weather conditions. For TandemX, I developed a system called TAF, which stands for TandemX Autonomous Formation Flying System, that does the autonomous navigation and control of the formation to acquire those geometries, keep them over time, reconfigure the formation to achieve the objectives with separations down to 300 meters. Now, we can use similar strategies by looking up for astronomy and astrophysics. And here the highlights is on a mission that has been conceived by my lab called M-DOT, the Miniaturized Distributed Occulter Telescope. Here we use 2 small satellites, a star shade, which has a 3 meters in diameter, that blocks the light from a star. It suppresses the light by 10 orders of magnitude, so to create a very deep shadow. And in the shadow, at 500 kilometers distance, we fly a tiny satellite. This is a 6U CubeSat. It's like a shoebox. That is the telescope that is able to detect very faint signals emitted by satellites, by planets that are orbiting around the host star. So to detect signs of biological activity, find life in the universe. Now, a mission that we are working on right now is called VISOS. It's due launched in 2027, funded by NSF. It is made of 2 small satellites, again, 6U CubeSats, shoeboxes, that form a virtual telescope with a 40-meter focal length that can achieve ultra-high resolution imagery of the corona of the sun with a resolution of 0.1 arc seconds, which is geometrically the same resolution of the James Webb Space Telescope, but at a fraction of the size and cost. So our work in the lab has designed the mission, the orbit of the satellites, and all the autonomy stack, all the algorithms for guidance, navigation, and control to align these satellites with centimeter accurate precision at 40 meters to obtain this high resolution imagery and resolve the energy release mechanism in the corona of the sun that are still not understood. Now, in addition, our algorithms, what they do is to guarantee the safety of the formation in the case of anomalies during the mission. And the third and last realm I want to talk about is when we look across space logistics. So this is an area of increasing interest because it's getting contested, congested, and it's economically very valuable. The problem is that with the launch of thousands of satellites every year and the lack of a space traffic coordination system, not only national, but at a global level, old-fashioned systems which are centralized and ground-based to guarantee safety are not sufficient anymore. So this safety feature has to move to the satellites, to the edge, in an autonomous manner. And this is the goal of the NASA Starlink mission. It's a swarm of 4 6U propulsive CubeSats launched in 2023 and still operational today to demonstrate autonomous swarming capabilities. My lab has developed the distributed optical navigation system for the mission that uses cameras on board each of the satellites to observe one another, use crosslinks to exchange measurements from the cameras, and do autonomous localization of the satellites with respect to each other, with respect to the Earth, and with respect to other objects. Here you see first of their kind results. These are images collected by one of the spacecraft on board, then processed in real time on board in order to identify all the objects that are in the surroundings and determine their orbits. So you can imagine the importance of these features if we want to move this kind of technology or distributed space system from just a tech demonstration to some trusted and critical infrastructure. And so this motivated me to start with my students a new company. It's a spin-off of my lab that commercializes my lab, that scales up NASA Starlink to the point that we use hundreds of these satellites deployed in low Earth orbit at different altitudes, so to obtain a neighborhood watch. Here you see high-fidelity simulation that show that if we use this sensor and compute on board, proliferated over a large number of satellites, we can achieve global coverage of the space object population, revisit times at the minute level, and orbit prediction accuracies for resident space objects that are far superior than what we can achieve today with ground-based systems. So to conclude, what excites me is not just the lab per se, but it's the flow outwards of the lab towards business. These are the startups that I advise, that I help creating by my former students, and policy through collaboration with Hoover, specifically the Stanford Emerging Technology Review, which is co-led by the School of Engineering, and my role at the United Nations as part of an expert group of the Department of State to help shape rules of space traffic control at a global level. So the final message is that the most important questions when it comes to science and technology cannot be answered by the ground alone or by single spacecraft. They can only be answered through the complementation of distributed space system, multiple spacecraft working together, so to serve as an extension of our terrestrial grid. The power grid, for example, as space-based solar power, or the data grid in terms of AI data centers. So thank you very much for the attention.